So thanks again for inviting me. I'm Venkat Vishwanath from the Argonne Leadership Computing Facility at Argonne National Laboratory. I'm a computer scientist at ALCF, and I lead the data science group here. And today I'll be talking about the ALCF AI testbed that we have established. And we'll talk about early experiences that we've had with applications. And in particular, I should point out scientific applications running on the AI testbed. The AI testbed has been established in joint collaboration with a variety of vendors, and we'll talk about the hardware that we have here, the software environments that we have, and the science that we've done here. I would like to point out that this is the work of many here. I would like to specifically point to work that Murli Imani, Corey Adams, Arvind, and others have done in enabling science applications of these systems, and also our partners at Cerebras, GraphCore, Grok, and Sambanova, who are part of this testbed, and we are working with a number of other vendors to incorporate novel AI systems and hardware as part of the ALCF AI testbed. So I wanted to start off with giving a brief overview of the Argonne Leadership Computing Facility. ALCF is a Department of Energy Office of Science user facility, and we provide world-class supercomputing resources to the open science community here. Our users come from national labs, academia, industry from all over the world to work on challenging science problems that they can't achieve in any other machine, and it requires the resources of large-scale supercomputers. We also have in-house experts from performance engineers, catalysts who are computational scientists, data scientists, visualization experts, as well as a large operation staff to enable science of these big systems. And as I pointed to you earlier, these resources are dedicated completely to open science. And a key thing that ALCF has been working on for the past few years is to enable science pipelines encompassing simulation, data, and learning on these large-scale supercomputers. And we offer various different pipelines and allocation programs ranging from Insight, ALCC, and the director's discretionary account, which helps you get started on these big systems. So going beyond just traditional simulations, which have been the core component of supercomputers, these systems that we deploy today help us enable science that encompasses simulation, data, and learning. And our upcoming system, Aurora, will have enhanced support for all these three areas. By simulations, again, we mean the traditional HPC simulations, which are PDEs. Data refers to very data-intensive applications. These could be either processing of data from experimental and observational data to seed perhaps simulation. It could be trying to analyze or visualize large-scale data sets. And again, I want to stress that these are for very data-intensive applications. And the third is deep learning and machine learning. So this talks about novel science where we leverage artificial intelligence for scientific discoveries. And we will talk some more about these shortly. Another aspect that we are witnessing today is a growing number of investments from various venture capitalists, startups, the tech giants in building AI accelerators that can achieve a factor of improvement over the traditional compute architectures for AI workloads. So here is an image from the AI chip landscape. There's a source from GitHub where you can refer to this. And in the past month alone, what we have seen is close approximately $1 billion plus investments from venture capitalists. We've seen investments in Sabanova and in Grok that have taken place in this past month, where the goal is to build AI systems and accelerators that can provide a, a multi-factor improvement for AI workloads. And one of the key uh, uh, evaluations that we as a supercomputing facility are interested in is understanding how effective are these AI accelerators for scientific workloads. Um, the traditional companies tend to target web scale or enterprise workloads, and we would like to understand how can they benefit scientific workloads? How do we architect systems that leverage these interesting accelerators and work collaboratively with these companies where we can improve both their hardware and software stack to meet the needs of future science workloads as well. So towards that, we have an AI pathfinding effort at ALCF at Argonne. And the goal is to really accelerate science by effectively coupling some of these novel AI systems, exascale supercomputers, and experimental facilities to uh, or to for scientific insights. And some of the key things that we are interested over here is to really understand how mature are the software stacks for these AI systems, the hardware uh, of these AI systems to meet the needs of science. How do we take the systems that are available and scale them and integrate them into a computational facility? And finally, we would really like to understand how can we apply them at scale to meet the needs of our science. So this is the key goal of our AI pathfinding efforts, and I'll describe some more in detail here. So as you well know, we have seen a surge of scientific machine learning applications, and you could think about this as, the ways that we have seen the surge is um, we want to design surrogate models where you could either replace, perhaps in part, a certain portion of your simulation with an AI-driven surrogate models to reduce the time to solution. Another part, another axis for this is data-driven models. You can think about the data that we get from sensors, from imaging experiments, from observational satellites or other systems, such as Internet of Things, where we take these data sets and build models from them. Some of the examples that you can see are in imaging, where we want to analyze the Bragg's Peak, where we try to build models from data sets that we get from experimental data. The third thing is where we look at co-design of experiments. Here is where you could look at intelligent sampling for either simulations, or in case of experiments, you want to intelligently sample portions of the sample under test. Now, these are just three examples, and real science applications are built by various combinations of these. And the goal for us is to really understand how do you design infrastructure to accelerate an AI for science, which comprises of all these three components over here. And as we build this, our goal is to see, if you look at tomorrow's supercomputing facilities, how do we take these novel chips that are being designed by vendors such as Cerebras, Sambanova, and other AI accelerator companies. And how do you really embed them as part of a big supercomputing facility? Would this be a separate, a disaggregated system where you could think about racks of these AI accelerators? Should we embed each of these chips as part of the compute node architecture? What kind of interconnect will be used to connect these systems together? These are all questions that we are trying to address and better understand as part of our pathfinding efforts. In addition to this, we are really interested in understanding um, how does the AI and AI at the edge component be incorporated as part of these facilities? Should it be part of the experimental facility? Should we have a component that is part of at the edge at the supercomputing facilities? Are questions that we are very much interested in understanding, and this will help us build effective supercomputing facilities for science going forward, and will enable both simulations and data-driven models. So towards this, we have built the AI testbed at ALCF, and as I mentioned, it provides an infrastructure of next generation machines with AI accelerators. You could go to the website ai.alcf.anl.gov and get a list of all the applications that we have, the systems that are available, and also provides you information on how to access and support this. And please always feel free to email me if you require any information or need assistance here. And our key goal is to understand, using using the testbed, how do you evaluate the usability and performance for scientific machine learning on these accelerators? So a key thing, again, I want to stress is we are interested in scientific machine learning on these accelerators. And as we understand the performance of scientific machine learning on these accelerators, our goal is, how do you incorporate this into a facility? So going from a chip level integration to how do you build a node level integration to perhaps a rack level integration, to how would it be tightly coupled as part of a facility? So these are the key questions that the AI testbed at ALCF is aiming to address. So as part of our testbed, we have 4 systems today. We have the wafer scale engine from Cerebras. We have the Sambanova data scale. We have systems from GraphCore. And we just recently received a system from Grok that is part of our testbed as well. And in addition to these 4, we have various ongoing engagements with other vendors to identify accelerators that we should incorporate and use as part of our testbed. So today I'll be talking about 2 of these testbeds. I'll give you some overview and insights on the performance of applications running on these testbeds. And I'll have some closing thoughts as well over here. So the first testbed I wanted to touch upon is the Medulla CS1 system. The CS1, as you can see, is a network attached accelerator. So if you can follow my cursor, the CS1 is a wafer scale engine, which is network attached to a switch. And we have 8 servers over here. One of them is a chief server, and we have 7 worker servers. Each of these are connected to the switch by a 200 gigabits per second Ethernet connectivity. And we have around 1.2 terabits per second connectivity between the switch and the CS1. And each of these servers are 20 core Intel Xeons with 192 gigabytes of DDR memory and 8 terabytes of an NVMe on each of them. The Cerebrus software basically runs in containers on standard CPU servers. The chief server is primarily in charge of handling the compilation, setup of the CS1 system, and also the management. The input workers are in charge of running the data pipelines and streaming data from to and from the CS1. The various training parameters such as data, the loss outputs, checkpoints are either stored on the input workers or on the network file system. The Sambanova data scale system consists of two SN10.8s. Each SN10.8 data scale system consists of a host module and 8 RDUs. RDUs are the building blocks for the Sambanova data scale, which is a reconfigurable data scale unit. So, and the RDUs internally are connected by a proprietary interconnect. And this helps one to really think about the system as a single monolithic system where you can write your program and the Sambanova data, the software stack takes the burden out of a programmer and helps parallelize your model across all the different chips that are available. And so you can run larger models as well as can fit larger data sets as well. The hosts are internally connected by InfiniBand, and this helps you to, if you have a data parallel problem, to scale across multiple hosts as well. In addition to the Sambanova and the Cerebra system, we also have the Graph Core as well, Graph Core IPU, as well as the Grok system. In terms of Grok, we have a node where we have 4 nodes that are available, and each node has multiple Grok cards that are part of it. So I'd like to briefly talk about some of the science applications we have on the testbed. We've actually worked with a number of science applications ranging from biophysics, cancer, high energy physics, neutrino physics, imaging sciences, and cosmology, and try to evaluate the efficacy of these AI accelerator on the for these science applications. So on the top left over here, you can see work that we are doing with cancer drug response prediction. And in this case, our goal is to identify what is the efficacy of various dosages of drugs and combination of drugs for the treatment of a tumor. So does it have an additive property or not? It's a key thing that we are trying to understand here. So in this case, we would take into account various drug descriptors, the genomic sequence of the patient. We would take into account the features of the tumor, the various dosage properties, and see what kind of reactions would we have in this case. I'll talk some more about the cosmic tagger, where we are trying to classify various pixels as either cosmic, background, or a neutrino. And some of the big challenge in this case is the size of the model and the size of the data set. Similar challenges are with the Bragg's peak example, where we are trying to analyze and identify the Bragg's peak in images that we get from a detector and try and correlate to these center of mass of the Bragg's peak to a diffraction frame that we have as well. And if we can accelerate this, we can perform, this will help us with near real-time experiments and will help us garner faster feedback. As you know, experiments take resources, time, and effort to set up. And if we can analyze them in near real time as we are running these experiments, it will greatly improve our productivity as well as the time to solution for the entire experimental run. In gravitational waves, we are working with our collaborators to understand a regression problem to predict various parameters uh, of the gravitational waves. And I'll be talking some more about protein folding, which we have been working on from the COVID-19 perspective as well. So these are just a sample of examples that we have been working with in a very diverse set of application domains, and there are several more um, that we have been working in addition to this. And again, the goal is to try and understand how effective are these AI accelerators for a wide variety of science, and from these, uh, it will help us better understand how to integrate these accelerators as part of future ecosystems. So my goal now is to talk about two applications that are diverse, uh, and will provide you with information about how, as part of the AI testbed, we are evaluating these science applications. The first that I'll talk about is the Stream AI MD adaptive MD simulations. This has been recently accepted at the 2021 PASC, which is the Platform for Advanced Scientific Computing conference. And the goal here is to really understand how to apply deep learning models to better drive adaptive molecular dynamic simulations in a streaming manner. And one of the big challenges in this is the real scale of simulations are really large, and they're limited by what is achievable on traditional systems as well as even specialized systems such as Anton. And we'll walk through some of the details over here. A key goal of the Stream AI MD is to accelerate the time to solution for understanding problems such as protein-protein interactions. And this has been critical for the COVID-19 work that we are doing, where we are trying to understand the protein-protein interactions between the NSP16 and NSP10 proteins. And if we can reduce the time to solution to understanding these interactions and folding, it will greatly enhance the time we may need to either come up with better candidates or to understand this phenomena in the situation here. So what you see over here is we have over here, if you can follow my cursor, are protein structures. And we take the structures and we come up with an input contact matrix, which is a 2D matrix in this case. And we pass this through a convolution variational autoencoder. And at the bottleneck, we are able to get latent embedding as part of, as part of the encoder. And this latent encoding is able to give us a representation in a high dimensional space. We run a number of MD simulations, and the goal is to try and understand, we run an ensemble of MD simulations, and the goal is to understand if the ensembles, or a member of the ensembles should be stopped because it's sampling a space that may not help or assist with the folding, or if there are any outliers that we really need to sample, or regions of interest that we need to sample. This latent space embedding helps us understand novel new configurations that we need to launch. So you can think about this as a way to adaptively sample and try and reduce the time to solution over here. And we will talk some more about this in the very next few slides. So the proposed approach that we have is we have the Theta GPU is a DGX3 based cluster that we have at ALCF. We have 24 nodes, and each node has 8 A100 GPUs as part of it. The system is connected by an InfiniBand based interconnect. And on each node, we run the OpenMM MD simulation package. And as you can see, here is where we are using OpenMM to run on up to 23 of the nodes. We use the data that we get from OpenMM simulations. These include the trajectories, and these are streamed out to the Medulla CS1. We run a training loop as part of the CS1, and the trained weights are then streamed back out to a single Theta GPU node where we are running the inference stage. And as part of the inference stage, the goal is to better understand which are the MD simulations that we have to continue, or which might be some new simulations that we need to seed. So it helps us generate these configurations that have to be launched or stopped so as to reduce the overall time to solution. And the key goal is to better sample the conformational space over here. So the role that we're using for the Medulla CS1, which is the Cerebrus wafer scale engine, is to accelerate the time to solution for training. And in this case, this is a novel case of how we are coupling a traditional GPU cluster with an AI accelerator to see if we can use the combination of these two to reduce the time to solution versus what it might take to just run it all on the Theta GPU system. The other aspect of this is to use the adaptive AI sampling techniques to see if we can reduce the time to solution as compared to a traditional atomistic simulation as well. So the data from the Theta GPU is streamed to the Medulla CS1. We run training on the Medulla CS1. The trained weights are transferred back to the Theta GPU, and we run an inference stage over here. From there, we predict the embeddings, and we try to look at a local outlier factor. And based on the outlier detection, we say we either choose to stop an ongoing simulation, or we can continue the same ongoing simulation or launch a new set of simulations as well. So we have some initial performance data from the Stream AI MD. This is for the NSP10, NSP16. And as I mentioned, we want to study the NSP10, NSP16 as the protein-protein interactions over here is key for understanding the SARS-CoV-2 proteome. What we see over here in this figure are the timeline that it takes to run these experiments. The blue gives us the MD simulations. The orange gives us the training time, and the green gives us both the inference time as well as the outlier detection time. And ideally, we should be able to overlap these so that we keep the simulations proceeding along and being able to search the entire space over here. So what we found is if you run some of the training on an A100, the challenges given the memory of an A100 is that it limits the batch sizes to 64, whereas we have been able to scale up to a batch size of 512 on the wafer scale engine. We achieve around 2260 samples per second on 8 A100 GPUs versus just using a single CS1, we are able to achieve around 8,300 samples per second for training. So this represents around a 3.7-fold speed up over here. If you scale out the training to use multiple DGX nodes, in this case, if we use 4 DGX3 nodes, we are able to achieve close to 8,000 samples per second. Though I have to point out, we are trying to build a coupled system to accelerate time to solution. So by taking some of the DGX nodes and sacrificing this for training, we are taking precious resources from the simulation side. So our key goal is to try and see what kind of a coupled system do we need to architect to improve the time to solution here. I would like to point out that in this case, we use a single precision on the A100s and a mixed precision on the CS1. We had some challenges with reduced precisions on A100 for this particular model, and we are closely working with NVIDIA to overcome these issues. So we are pretty confident that as the software stack on NVIDIA improves, as well as the software stack on the CS1 improves, we'll be able to revisit this and make fairer comparisons going forward. So in terms of, so what we talked about were performance numbers in terms of time to solution. What we're going to look at now is the performance in terms of science impact. So a key goal that we're trying to see is if you take an 8-hour experiment, our goal is to see how far apart are you from the native state, native equilibrium state that you would have achieved if you had just let the MD simulation run for a period of time. So the closer you get to the native state, in this case, the minimum RMSD configuration was 2.43. So the closer you get to 2.43, the better is your solution from a science impact. So if you look at an 8-hour experiment, with the CS1, we were able to achieve closer to the native state as compared to running it on, running the training on 8 A100s over here. And if you just look at the time to solution here, what we observed was if you take 18 for an experiment of 18 hours, we were able to achieve a minimum RMSSD value, and it would have taken us approximately 923 hours for an equilibrium ensemble simulations on an A100s. This is the case where we have where we just run the ensembles till it reaches the equilibrium state of the minimum RMSD value without any adaptive sampling. So in this case, we would achieve a close to 50x speed up by both using the adaptive sampling as well as using novel AI accelerators for the training. Discuss a wider range of applications across these systems as well. And with that, I would like to say that this work has been funded by the Argonne Leadership Computing Facility, a Department of Energy Office of Science User Facility. And I would thank you for your time.